So today we are going to talk about Newton's 3 laws. We will do some, that's Newton's second law. No, we won't do projectile motion. That won't be for a couple of chapters, I don't think. Because we're still all in one dimension. We don't have any angles or anything to add into this yet. So forces can be a push or a pull, and they cause acceleration, stretching, bending, squeezing, change in direction. Forces are vectors, not scalar. Put the computer away. Oh. So in this right here, we have our external world is the table, the book is in our system, and their hand is pushing on the book. And this is what is called a force diagram. And we have the forces that are acting on the book drawn here. We have the force of the hand of the book because the hand is pushing across the table. The table is pushing up on the book, and the book is pushing down on the table. These are equal and opposite, so there's no movement in the vertical direction. There's only movement in the horizontal direction because there's no net force balancing out that force of the hand on the book. So there's lots of different forces. We are going to talk about mostly just mechanical forces. And there's also gravitational force, which are attractive forces between all objects, not just between the sun and the planets or the earth and the moon. All objects have some sort of gravitational pull on each other. Most of them are very small and you aren't detectable. But like Sierra and Dolores are attracting each other because through gravitational pull. Very, very tiny, though. Not enough to change anything. Electromagnetic forces, that when particles with electric charge, they hold all the matter together, like ions, when they form compounds, positive and negative cations and anions. Those are electromagnetic forces. Strong nuclear force holds the particles of the nucleus together because in the nucleus we have all protons, which are all positively charged. So the strong nuclear force is what holds those positives in tightly together. And the weak force is involved in radioactive decay. Free body diagram I kind of showed you with that book and table picture. It's a pictorial model, and it represents the forces and the motion of that system, and we will probably be drawing a lot of free body diagrams. It's good to show all the forces that are being applied to an object. So Newton's first law, Newton did a lot of studies on force. He said that an object in motion or at rest will remain in that state unless acted upon by a net external force. So the desk here will stay sitting or stay standing still as long as no one puts an external force on it. Now if I push the desk, I have an external force going in one direction with no force balancing out in the opposite direction, so it will move. Are there forces acting on the desk though? Yeah. There are. We have the force of gravity pulling it down, but the floor is pushing back up on it, and they're equal, so they're balancing each other out, so there's no movement on it. So there are forces acting on it. This is also called the law of inertia, and sometimes there's more than one force acting upon the objects. It can produce kind of a tug-of-war type thing, but you could have something pushing and pulling on the same object, and you would have to add them together in order to figure out what kind of net force there is. Newton's second law states that the acceleration of an object is directly proportional to the net force on it and inversely proportional to its mass. So they can sum it up in an equation that the net force, that sigma means net, so the sum of all of the forces is equal to ma. And we will split all the forces into directions. So all the horizontal forces are separate from the vertical forces. Acceleration is always in the same direction as the force. If I push this desk to the left, it's not going to accelerate up, right? It's always in the same direction that you apply the force. And the units of force are Newton. If we take mass units are kilograms, and we multiply by meters per second squared, which is acceleration. So kilogram meters per second squared is a Newton. We will be using that equation a lot. It's an easy one to remember though, right? F equals ma. Newton's third law, every force has an equal and opposite reaction, which are called action-reaction pairs. So even when you're picking up a bowling ball, the force is coming up of you picking up the bowling ball, but there's also a force of the bowling ball down. It's not a balanced force, because if you're picking it up, you have some sort of you must have more force going up than the ball has coming down, because you would accelerate upward. Only the forces acting on that ball, though, would determine the acceleration of the ball. Okay. So we have some problems here. I don't know why they used that strange name. Is that a Spanish name? No? It might be Anuja? But she's holding a stuffed dog with a mass of 0.3 kilograms when Sarah decides that she wants it and tries to pull it away from Anuja. A stuffed dog, like a stuffed animal? But in dog shape, yeah. Not a real dog. If Sarah pulls horizontally on the dog with a force of 10 newtons and Anuja pulls in a horizontal force of 11 newtons, what is the horizontal acceleration of the dog? What is our net force? Let's draw B1 in which direction? If this is our puppy. I don't know. Okay, so there's our dog with the floppy ears. Okay, there's the dog. And we have someone pulling it this way, and she's pulling it this direction. And let's make this 11 newtons, and this is 10 newtons. So what's our net force? To the left, we have 1 newton to the left is our net force. So our net force is equal to ma, correct? And we're looking for acceleration, so it'd be F, our net force, I should say. Net force divided by m is equal to A, correct? So we have 1 over 0.3 kilograms. Now, because a newton is a kilogram meters per second squared, we have to make sure that all of our units are in kilograms, meters, and seconds. The MKS system, sometimes it's called, meters, kilograms, and seconds. So since 0.3 kilograms, already in kilograms, so we can just leave it. What do we get for our acceleration? So 3 point, okay, how many significant figures should we use? Yes. No, but it's subtraction, so that would be just 1. So we just have 1 significant figure, right? Oh, 10.0. Yep, so it'd be 1.0. 3.3. Yep. Meters per second squared. Good. next one. What net force is required to accelerate a 1,500 kilogram race car at 3 meters per second squared? So now we have net force. We would just multiply them together, right? Equals MA. So we have 1,500 kilograms times it by 3.0 meters per second squared. And we would get 4,500. How many significant figures we want? How many does this number have? 2. So there'd be a decimal point after it would have 4. I'm not going to get real technical with your significant figures in this class, but I want you to think about it. That's why we should do it that way, okay? Try to do the best you can at getting your answers in significant figures. And the next one, when a shot putter exerts a net force of 140 newtons on a shot, the shot has an acceleration of 19 meters per second. What was the mass of the shot? So it would be the net force multiply or divide by the mass, or the acceleration, I guess. Divide by the acceleration to get the mass. So that would be equal to 140 divided by 19. What do we get? What is it? What?
That one right?
Oh, I was looking at your calculator and I was like, what in the world is
no.
So 7.4 kilograms? Is that what you guys got?
Mm-hmm.
Okay, good. So this is an easy equation to use, right? It's going to be more difficult when we include the equations from last chapter in here. Like this next one. So an artillery shell has a mass of 55 kilograms, and the shell is fired from a gun, leaving the barrel with a velocity of 770 meters per second. The gun barrel is 1.5 meters long. Assume that the force, and thus the acceleration of the shell, is constant while the shell is in the gun barrel. What is the force on the shell while it's in the gun barrel? So to find force, we use the net force is equal to ma. It's looking for the force. We know the mass. Do we know the acceleration? Can we find acceleration? Yes, because we know what? The initial velocity was 0. We know the final velocity was, and we know d is 1.5. So now we could find acceleration. We can use VF squared equals VI squared plus 2AD. So this is 0. So let's put the numbers in here. 770 squared is equal to 2A times 1.5. So what do we get for acceleration? Well, if you think about going from shooting something out of a gun, we should have really high acceleration, shouldn't we? So I'd say we should get something high. What do you get?
That big number, but would you round that up to 20,000?
We need 2 significant digits. This isn't a measurement. This is just a number.
Oh yeah, but like if you round that up, then this is 0.
So then it's 200,000. To show we have 2, I would use 2.0 times 10 to the 5th.
Yep.
There we go. That way we can show we have 2. You can write it 200,000 just for future reference. You can write it with 200,000 and put a line over the 0, and that shows that that's significant. This is 2. Why 2? Because we're dividing. You don't get that same answer? Yeah. What do you get that too? Did you divide by, you divided by 1.5, you squared, can I see that? When you did 770 squared, did you push the divide right away? I think it's taking the squared, the 2, and dividing that by the 1 time.
Yeah,
so if you put that in parentheses.
No, talk about like final.
Okay, how'd you do it? Show me again. Okay. Divide, yeah.
11 million.
Okay. Yeah. Okay, so you got that number, right. That when you round to 2 significant figures, you'd round 1 9, but the 7 would round the 9 up to a 2 also. Okay. So then that's how they got that. So yeah, that's the number they got on their calculator. Okay, so then we would take that acceleration times the mass is 55 kilograms. So what do you guys get to the force? 11 million. Wow. 11 times 10 to the 6th Newton.
Can we see our tests today?
Yes, Zach is taking it. He took it too.
Okay.
Yeah. So questions on that, how we use different equations to get to a point? Okay. Just build on what we already know. Yep, this will be the last problem. Imagine a spider with a mass of 7 times 10 to the negative 5th kilogram moving downward on its thread. The thread exerts a force that results in a net upward force on the spider is 1.2 times 10 to the negative 4th newtons. What's the acceleration of the spider? How about you guys figure that one on your own and see what we come up with? I've had these up here for a long time, and they have a bunch of physics formulas on it. If you guys want them, keep it. Otherwise, you can trash it. Might be helpful. Lots of formulas.
Is there any important things I should know for that? I'm taking it tomorrow.
SAT? I don't know what. I have no idea what they ask on there. I would say the stuff that we've done are more a lot of the basics. What do you guys get for the answer? You guys all agree on something? Times 10 to the, or just 1.7? Oh, okay. Yep. I guess that makes sense there. Everyone agrees with that? Very good. That is all for today, and then Monday we'll start an experiment on Newton's second law, the F equals ma. We'll do that.